Yes, we can hear and see well.
Okay, perfect. So let's go. So this is joint work with some colleagues and a student at Gilles about the computational intelligibility of Boolean classifiers. So the very starting point of this work was this following question: what is a good classifier? And it is not a very easy question, just because there exists a number of evaluation criteria that can be considered to assess the quality of a classifier. A very common standard one is accuracy, of course. And accuracy can be defined as the probability of correctly labeling any given instance. Okay, so maximizing this probability is minimizing the classification error. And in practice, this classification error is estimated on a test set. But in our work, we are focused on another important criterion, that is intelligibility. Such an idea of intelligibility is of the utmost importance when dealing with critical systems and high-risk applications. For such cases, we need to be able to enter into the black boxes, okay, to get explanation, to achieve some verification tasks. This is really crucial. The difficulty for this intelligibility issue is that there is no agreement on the meaning of intelligible. Okay, in fact, informally, we can try to define it as the capacity to derive from the classifier some useful information. The point is that useful typically depends on the explainee, the person who actually uses the classifier, who asks for explanations, for instance. Okay, so if you want to go a step further and define a bit more formally the computational intelligibility of a classifier, we can try to point out a number of explanation and verification queries about the classifier itself. So explanation queries are about explaining why a given instance has been classified by the classifier as it has been classified, or not classified by the classifier as expected. And you can see here that the user takes some place in this issue, okay? And this is also the case for verification queries. Here, the purpose is to determine the extent to which classes as identified by the classifier comply with the expectations of the user. Okay, the user may have some expectations about the classes, and we want to verify whether those expectations actually, in some sense, hold in practice in the classifier. Okay, so this definition of computational intelligibility of a classifier can be lifted to families of classifiers, also known as machine learning models. And in our study, we are focused on Boolean classifiers. Okay, so we start with Boolean features, and we consider just actually two classes, a class of positive instances and the class of negative instances. And as we will see later, with respect to the results obtained, this is without loss of generality. In the following, I will use a toy example to illustrate the concepts. The problem here is to recognize some specific roses, common holyoaks, from other roses using 4 Boolean features. The fact that the plant has a deciduous foliage, has heart-shaped leaves, has large flowers, and has a light green stem. Okay, and a classifier here is a Boolean function represented, for instance, in the Carnot map as provided on the slide. Okay, so if we want to learn such a classifier, we can use take advantage of many different machine learning models. Here is a very simple one, okay, a decision tree. So we have a decision tree of the 4 features. The leaves are labeled with 0 or 1, 1 when the instance is classified as a positive instance and 0 otherwise. Okay, so this is quite standard. And if now we want to define more formally the computational intelligibility of a classifier, we need to make precise those explainable AI queries that will be used. Okay, And in fact, in the literature, and especially in the previous paper last year in KR, I have pointed out a couple of such XI queries. There exist also other queries of that kind. I do not have time to detail them. I will just focus on two. One explanation query deriving one prime implicant explanation, so DPI, and another one verification query identifying monotone features in a given class, or IMO. Okay, and so given such a set of XI queries, we can now define formally the computational intelligibility of a classifier as a subset of those queries that are tractable for the classifier. Okay, this is the idea of the capacity. The capacity is computational. Okay, so DPI, we start with the notion of abductive explanation. So explaining why a given instance has been classified as such by the classifier. And a PI explanation actually does not contain irrelevant features. So for instance, if we consider the instance where feature x1 is set to 1 and the other features are set to 0, to false, okay, this instance is classified, as you can check here, as a negative instance, okay? And if we want to derive a prime implicant explanation, you will remove all of those features that are not useful to get this class, okay? And here you can easily check that whatever the values given to features x1 and x4, you will get the same class of negative instances, okay? Whatever the value of x1 and the value of x4, okay? So x2 set to false and x3 set to false is a prime implicant explanation for the input instance here, given the classifier. A verification query now, the monotonicity of some query, of some features, sorry. We're going to say that a feature is monotone for a class, let's say, of positive instances. If and only if, when you consider an instance that is classified as a positive, and the value of the feature is 0, so the feature is not present. If you consider the same instance, but now you switch the value of the feature, okay, the feature is set to 1, then you obtain an instance which is classified in the same way. So classified positively here. And for instance, in our example, it is easy to check that x2 is a monotone feature for the class of positive instance. It means that if x2 is set to false, in order to get a positive instance, you have to set x1, x3, and x4 to true, okay, to 1. If you do the same when x2 is set to true, okay, you will get as well an instance that is a positive instance, okay, from the point of view of the classifier. Okay, so the goal and the contribution of our study was to determine the computational intelligibility with respect to those, the previous queries, of a number of models, decision trees, but a number of other ML models. Okay, and let me start with decision trees. Decision trees are typically considered as intelligible because, in fact, an abductive explanation, the so-called direct reason, can be associated with each prediction made. Okay, and it explains it somehow. For instance, if you want to classify the instance where x1 is set to true and the other features are set to false using the decision tree here, okay, you just follow the path that is here, okay, the only path that is compatible with the instance, and you get the label 0, meaning that the instance is negative. Okay, so the direct reason here is x1 set to true, x2 and x3 set to false. Okay, it corresponds to the path that is followed. Such a path can be computed in linear time, given the instance and the tree, but it does not always coincide with a sufficient reason. However, it is quite easy to generate a sufficient reason from this direct reason, okay, using a greedy algorithm. We can do it efficiently using a polynomial time algorithm.
Yeah, 2 minutes left.
Okay, in fact, decision trees are computationally intelligible models for many more reasons. One of the key results in the paper is the fact that all the previous XI queries okay, can be achieved in polynomial time when the classifier is a decision tree. Okay, so now what about the other machine learning models? In fact, they appear as far less computationally intelligible than decision trees. And the second key results in our paper is the following. Okay, all the previous XAI queries are in fact NP-hard in the broad sense when the Boolean classifier is one of the other ML models we have considered. Okay, so there is a sharp separation between decision trees and the other ML models that have been considered in our study. Okay, and for us, it was a bit surprising because at first sight, decision lists look closer to decision trees than, for instance, to multi-layer perceptrons. Okay, and in fact, it is not the case that they are closer from the perspective of computational intelligibility. It was quite surprising. Of course, there are a number of perspectives for this work. For instance, considering other machine learning models, we have focused on some of them, but we do not consider, for instance, so far incomplete propositional fragments. There are some of them are interesting because they are pack learnable. We could also improve the picture by considering other XAI queries. We could also try to derive more fine-grained complexity results. We just consider NP-hardness or tractability. We could do something actually more fine-grained. And it would be also interesting to evaluate in practice the hardness of those XAI queries for various ML models. Okay, in this work, we just consider, say, we just use a theory-oriented approach. And okay, that's it. Thanks a lot.